Hi, can you hear me online?
Yes, sir.
Yes.
Okay. मेरे कीबोर्ड है करे नहीं one thing I'm not sharing my screen. Can you see my screen? Oh, just wait for 2 minutes. Okay, so next Sunday I will have one practice test for you. It will be like IOQM, maybe of less duration. So same format, like you'll have to write the answer as 00 to 99 numerical answer, but maybe number of questions and time will be proportionately less. Almost it will be identical to the selection test that you gave. So kind of a similar pattern you can expect. Okay. And it will not be necessarily based on what we did in the last 3-4 weeks because we have been only doing one topic, which is geometry of circles. But finally in IOQM, all topics will be equally important. So you will get practice to do all those things. So what you should focus on, as now you know that after 1 week you have an exam. So what are the things that you are going to do to prepare for that? Because these are the same things which we will do before the actual IOQM or RMO exam, right? So how should you prepare for an exam like this? And note that Olympiad is the kind of topic where you cannot mug up at the last minute that there is some topic I can quickly do, which is going to be important. And the last 3 days I will get it. So forgetting about learning new theory, whatever theory you already know, your responsibility is to become really good at what you know. Become an expert at what you know. Leave aside the things that you don't know, because most of the things that you know are sufficient to do Olympiad like IOQM level problems or pre-RMO level problems. So your focus should be what can I do to improve my problem solving ability based on the topics that I already know. So first, most important thing is revision. Okay, so make sure to revise everything that you know, because there are many theorems which you may have heard once in some lecture, but you have lost track of them, or you don't realize that they're important theorems. Something basic like Pythagoras theorem, which can be generalized to other things like Stewart's theorem, for example. So these kind of basic tools will be useful for you. Other similar things in number theory, for example, even if you are not done number theory formally, you know the basic idea of divisibility, division, remainder, GCD, LCM. So these things that you know. So just keep all of these things nicely organized in your mind. And to do that, first they have to be nicely organized on paper, right? Something which I already said last time, that if you are going to study from your own 200-page notebook, it will be very hard to find that one page which has that important property. You may miss it or you may not realize the importance of it. So make sure to document these important things as a separate, either a separate file or separate section in your notebook. So that kind of toolkit is very important. Okay, so revision of the problem solving ideas, then the actual problems. So what do I mean by this? So just go back and look at the selection test paper, which everybody has attempted, right? And you know which questions you're able to do, which you are not able to do. Have I sent you the hints and answers? Okay, so I'll do it immediately. So refer to that and find out which questions I could not do. Looking at the hint, now I'm able to get it. And now think to yourself that why did I not think of this particular idea? What is the motivation that will lead me to think of this solution? So have this conversation with yourself, and so that next time a similar problem comes, you should think of the right idea automatically. So you have to put yourself in that train of thought. Okay, so for that, getting exposure to problems is an important thing. And maybe one more topic, which is kind of, in a short term it may seem like a waste of time, but in the long term you have to do this. You have to also construct new things. So construct new problems, ideas, variations. So don't just solve one problem, because the same problem will not get repeated. What will get, maybe next time a slight variation of that problem will come. So if you can think of those variations yourself, that okay, this was a problem involving some maybe x square something. Can I modify it and make it for x cube? Or can I add one variable? Can I reduce one variable? What is the most general form of this question that I can solve? So think of all of these ideas, because, and I know honestly that is how I design question papers, because I'm going to design a question paper for next Sunday. I've already started. So some questions are original, which I think of the first time that okay, this idea. But sometimes you have to borrow ideas from your old papers, right? So I just take an old question, modify it slightly, and put it as a new question. So that happens all the time. And so if you are prepared for that, you will do better at the exam. Okay. So keep all of these things in mind, and try your best to prepare in this way for the coming practice test next Sunday. And so if things go well, then you know that you're on the right track. Even if let's say you don't score as much as your expectation, still learn something from that. Okay, what did I do correct? What did I do wrong? And try to correct and improvise. After this practice test, I don't know if we have enough time to do one more practice test. So because the IQM is right in start of September, right? So there is very little time. So you have to use this opportunity to maximize your preparation. Okay. And again, don't worry that I don't know this topic, I don't know that topic. Your worry should be that I heard about this topic, but I have forgotten about it. That is what you should be worried about. Or I know this topic, but I don't know how to apply it in problems. So any such doubts that you have, bring it to my attention. That let's say you have that I want problem solving practice on this particular topic, then I can try and find sources of problems for you to solve that. Okay. So that is how you should prepare for the exam. And rest of the details, like at what time the exam will be, whether it will be online or offline, those details I will work out and I'll announce on the WhatsApp group. Most likely it will be hybrid. That is, those who can come in person and write the exam here, please do that. Those who cannot, you will write the exam at home. Actually, I'm going to prepare a bubble sheet for you. Okay, just like the exam. So you're not going to write just the numerical answer. You're going to fill the actual boxes. Okay, so even if you are going to appear from home, you are supposed to take a printout of that bubble sheet, fill it up, and send me a scanned copy. Okay, so that you get the full exam environment. And as far as possible, those who are in Pune, try and manage to actually come here and write the exam, because that gives another seriousness to the whole activity. There are no other distractions around us. So yeah, that is what I would suggest. Okay, so that was about the exam. But coming back to the other end of the spectrum, which is not exam. So as I mentioned last time, that I will be talking about trigonometry today. So I'm very excited about today's lecture, because trigonometry is something which has so many implications. Today we are going to look at trigonometry from at least 3, 4, 5 different angles, that how different people look at trigonometry, and each of them has something interesting to teach us. Okay, and at the end of the lecture, if you find this is something interesting, fascinating, which I want to learn more about, then my job is done. So my job here is not today to show how trigonometry is useful for solving Olympiad problems. It is useful, but that is only one small part of it. It's like the tip of the iceberg. So we are going to look at the whole iceberg today, and then of course how to use that in Olympiad is going to be part of it sooner or later. So what to do trigonometry? First, I need to establish some common ideas, which we all know as such, but need to sort of crystallize them in a different language. So one of the things is coordinate geometry. Okay, so we need to understand coordinate geometry very well before we look at trigonometry. Or rather, before that, kind of the school level. So what I'll say, the first like the level is the school geometry approach to trigonometry. Okay, so this approach can be explained very easily. This is what I already explained last time, so there is nothing new. That basically what we said is that if you have any right angle triangle, okay, with some fixed angle theta, and if you have any other right angle triangle of the same family, then this opposite side upon hypotenuse, right? This ratio opposite side upon hypotenuse, this does not change regardless of which triangle you take of this entire family. So instead of saying that I'm talking about this particular triangle, I am interested in this ratio no matter which triangle I choose. So we decided to give it some name and we called it sine of that angle, sine of theta. And similarly, we define cos theta and things like that. Okay. So understand that this is a kind of notation which we are creating to make our calculations simpler. That instead of writing a ratio every time, I can write just sine theta, and that makes it easier to manipulate that ratio, relate to triangles with each other. Like for example, in the same diagram, you may have a different place where the angle theta is there, and there may be some properties related to each other which you will not ordinarily discover, but because the same theta is there, so the sine theta is also the same, and therefore something happens. Okay, so these kind of connections are made possible if this interpretation of trigonometry. So in the very basic approach, sine theta is just opposite side upon hypotenuse. What is cos theta? Cos theta is the adjacent side upon hypotenuse. So adjacent side means this one. So for example, if I'm talking about this triangle, then this is the adjacent to the theta. So this is the adjacent side and upon the hypotenuse. Okay. So immediately based on this definition, do you see some property that sine and cos will satisfy? Like if you take one particular triangle, right? If I talk about this triangle OAB, then sine theta is AB upon OB, and cos theta is OA upon OB. So what properties can you think that these two lengths satisfy, given that it's a right angle triangle? Sine theta is cos 90 minus theta. Yes, correct. So if you observe, if and this angle is theta, then this angle is 90 minus theta. And for this angle, the opposite side is this one, right? So now if I write sine of 90 minus theta, I should write 90 degree minus theta. Okay. Why, I'll come to that later. So that is now OA upon OB, right? Because the opposite side to 90 minus theta is this one, right? Which is cos theta. So basically sine and cos are like complementary to each other. Sine of one angle is the cos of the complement angle. And you see cos is also the same. Cos of one angle is the complement of the other angle, right? So sine of theta is cos of 90 minus theta. And cos of theta is sine of. Anything else? It's a right angle triangle, right? So yes, correct. Correct. So as Anushka is pointing out that if you take the square, it's a right angle triangle, so you would like to apply Pythagoras theorem somehow. And so if I write Pythagoras theorem in this triangle OAB, I know OB square is equal to OA square plus AB square. And so if I divide everything by OB square, I will get 1 is equal to Okay. And what is this? This is nothing but OA upon OB, which is cos theta squared. And this is sin theta squared, right? So this is nothing but cos of theta squared and the sine of theta squared. Okay. So these three basic results, that this is equal to 1 and these two. So these are the three most basic things that you can observe from this diagram. Okay. And there is one more ratio that we like to define, which is called tan theta. Do you know how that is defined? So tan is actually sin theta upon cos theta. Okay. So we define tan theta as sin theta upon cos theta. Or equivalently, you can see it is the same as opposite side upon adjacent side, because the hypotenuse will cancel, right? So it is opposite side upon adjacent. Okay. So in our diagram, for example, it is going to be AB upon OA. Okay. So at the very basic level, this is all that you need to know, that these three topics, these three formulae or identities, and the definition of sin theta, cos theta, and tan theta. So this is what I'll call the school geometry version of trigonometry, and which is also very useful. We don't want to discount it that this is not useful, but we can do much better. Okay. Because one limitation you will see is that all this is fine when this angle theta is acute angle. What about obtuse angle? Because if I want to say define sine of 135 degrees, then I'm talking about drawing a triangle whose one angle is 135, one angle is 90 degrees, which is not possible, right? So you see there are some limitations of this approach. So we would like to break free from those limitations and do something much more wider in scope. So to do that, have you copied that? Okay. So for that, as I said, first we need to really understand coordinate geometry very well. So how do you look at coordinate geometry? What is the purpose of coordinate geometry? In your words, can you tell me? What happens because of coordinate geometry? What are you able to do? Yeah, we're able to describe shapes like parabola, yes. But describe in terms of what? Equations or numbers, I would say. So most important function of coordinate geometry is that we can assign numbers to represent points in any space, any set. So for example, in the plane, we require two numbers, right? X coordinate and Y coordinate. In 3D space, we'll require three coordinates, right? X, Y, Z coordinate. But actually, if you look around you, coordinates are everywhere. So for example, there is one more coordinate system which you knew from very early age. Do you know what coordinate system? Do you already know? What? Number line, yes. Any real world coordinate systems which we use all the time. GPS or latitude longitude. Do you realize that latitude longitude is a coordinate system on the shape of the earth? Because if I give you those two numbers, you know exactly the position of any place on earth. Okay, so coordinate geometry is actually not just about 2D coordinate geometry. There are many versions of that. And last time I talked about how coaxial circles lead to a different coordinate system. Okay, so it's a very broad topic. Okay, so fundamentally, coordinate geometry can be looked at as two ways. So one way is that it shows a correspondence between points. Actually, it's more general than points, but let's say for now we are talking about points and numbers, or sometimes pairs of numbers, pairs or triples of numbers. Okay, so this mapping between a region of space and a set of numbers, that is what coordinate geometry allows us to do. So for example, in the basic formulation, plane XY coordinate system, I give you a pair of real numbers and that describes a point in the plane. Or if I point to any point in the plane, you know that there are two real numbers associated with that. So there is a one-to-one mapping between the points and the pairs of numbers in that case, for example. Okay. So this is one description of coordinate geometry. I would like to talk about one more description, which is that coordinate geometry also is a recipe or procedure to reach any point. Okay, what do I mean by this? So let us take the example of the Earth, latitude, longitude. So when I say, let's say some position P is located at 30 degrees north, 20 degrees east, for example. So the way I look at this is that first you start with the Earth, right? This is actually the Earth is not like that. It is tilted, but for now I'm just drawing it very simplified view of Earth. Okay. Okay. So do you realize, maybe you never thought of this, there will be some place on Earth which has coordinate 0, 0, 0 latitude and 0 longitude. Does anybody know which country that place belongs to? Sorry? No, London is the prime meridian. So that is the axis of 0 longitude. But along that, so UK is located quite up in the northern hemisphere, right? Close to the equator. So there is one point where so let us say this is that 0 degree longitude, and this is my equator. So where the 2 points meet, which has a coordinate of 0, 0, it will be very fun thing to stay there. If you have to tell your address, what is my address? My address is 0 north 0. I cannot even say north, right? 0 degrees latitude, 0 longitude. Okay. There is something interesting about that place. You can Google it and find out some interesting things about that place. Actually, it is called a null island for some reason, and it is not an island at all. Okay. So, but what I want to say is that what this tells me is that a procedure by which I can reach any point starting from there. Because what am I saying? First 30 degrees north, which means I'm going to tell myself travel 30 degrees north. So, I mean, considering the origin of the Earth, the center of the Earth, I have to first take a 30-degree angle. Okay. So this is my 30-degree north. Okay. So wherever I land, so you see, I'll land on the latitude, which is at 30 degrees. Okay. So the important thing is that all the points on that latitude have the same 30-degree coordinate in terms of latitude. Okay. So we can call them the iso coordinate curve. So all the points on that have one coordinate common. Okay. So all the latitudes are iso coordinate in terms of the latitude. And you see all the meridians. So meridians are these, right? So these kind of, along which the time zones are marked. So these are the iso longitude curves, that any point along that line has the same longitude. Okay. So you can travel along one. So first I'm going to travel like this from here to here, and then I'm going to take 20 degrees east. So I'll be go, let's say 20 degrees east. Okay. So from my starting point of the origin, I could reach this point based on this recipe. Okay. And this is how you can look at any coordinate system. So for example, in 2D coordinate geometry, you can think of it this way, that when I have a normal coordinate system, and I say I'm interested in the point 2, -3. So the recipe that describes to me is that first take 2 steps in the x direction. Okay, so this 2 is nothing but take 2 steps in the positive x direction. Okay, so I'm going to take 2 steps like this, and then travel -3 in the y direction. So -3 means below the line, right? So wherever I land, that is my point 2, -3. Okay, so in a way, you can look at this as a recipe to reach this point. Okay, but as it turns out, there can be more than one way of reaching this point. For example, why don't we do this? I'm going to describe a different way of reaching. So I am first facing the positive x-axis. First, I say turn clockwise by some angle. I don't know how much this angle is. Okay, I'm just going to call it theta. Okay, so turn towards the right by angle theta first. Okay, so I'm facing this direction now, and now I want to say walk ahead by this much distance. Okay, so whatever is that angle and whatever is that distance, those two numbers, so r and theta, can also be used to reach this point. Okay. So except that I should not write it this way. So the general notation which is used is like this: r angle theta. So you see, this is one more recipe to reach the same point based on the distance from the origin and the angle that it makes. Okay, so there is not one coordinate system. There are multiple coordinate systems. So this is what we normally use, like x and y, right? That is what is called a Cartesian coordinate system, because the mathematician Descartes was involved in developing that. And this is what is called a polar coordinate system. Okay. So let me just, I'll choose a different point because this does not illustrate it well. I'll choose a point in the first quadrant only. What do we need? But if we no, yeah, but yeah. So I mean, for example, just to take one more example. For example, so some points will be easier to describe in Cartesian system and some point will be easier to describe in the polar system. So for example, can you tell me the, so suppose I'm talking about the point 1, comma 1 in Cartesian coordinates. Okay. Can you tell me what are going to the polar coordinates of that point? Root 2. Correct. Because the firstly, how much is the angle I need to turn to face that point? 45 degrees, right? Because this is a 1 kind of triangle. And then how much do I need to walk in that direction? Root 2. So I can describe the same point as root 2 angle 45 degrees. Okay. And you can derive formula to convert back and forth between the two. Okay. If I know the Cartesian coordinate, I can convert it to polar and vice versa. Okay. So this is one more coordinate system that is existing in the plane. But we have to establish one convention, which is that we always measure angles starting from the positive x-axis and we always go anti-clockwise. Okay, this is something that we established. So for example, if my point is over here, okay, now there's ambiguity. Should I talk about this angle or this angle? Okay, so the convention that we established, we always start with the positive x-axis as the 0 degree. Okay, so this is the 0 degrees and we always go anti-clockwise. So basically this is 0 degree, this is 90 degree, this is 180 degree, this is 270 degree, and 360 degree comes back to 0, right? So we don't have to repeat that. So in fact, we will never, the angle component, we won't go beyond 360. We'll always keep between 0 to 360 degrees. Okay. But in this way, every point in the plane can be described. Okay. Okay. So the question is, what is all of this for trigonometry? So actually, the way, if you look at modern textbooks, how they define trigonometric ratio, sine and cos, to solve this problem, that I want to define trigonometry for acute angles, obtuse angles, negative angles. So to do that, I'm going to use this approach that uh, actually before that, I need to talk about one more thing. So that is the units of measurement. Okay. So, degrees, we used to measure angles, 90 degree, 180 degree, and 360 degree is one full revolution. But is there anything magical about this number 360? Why was it chosen? That whoever created geometry initially, why did they think of using this number 360? Any reason? Maybe it was somebody's birthday, or
Well, because it have more devices.
yes, it more devices, right? So it is very easy to divide 360 into smaller parts, like it divisible by 3, 4, 5, 6, 8, 9, 12, 10, so many devices. So the convenience was the reason why that 360 was chosen. But mathematically speaking, there is nothing special. I could have chosen any number I want, right? So what, at some point mathematicians decided to do, and there are reasons for this beyond just, they wanted to do this, is that they defined a new unit of angle, okay, called radian. Radian. Okay. So radians and degrees are two different ways of measuring angles. And degrees I show by, how you show with a small circle, right? Like I write 45 degrees. Radians are shown by a small c. Okay. So whatever is the number. So for example, 45 degrees happens to be pi by 4c. Okay. Why suddenly where did pi come from? So I'll explain. So actually the radian is defined in this way, that whatever is the radius of your circle, okay, you first consider a circle of any radius you want, and you take an arc of that same radius. Okay, so if I consider an arc, the arc length I want to be of that same radius. And you see this diagram doesn't depend on the scale. Like if I choose a circle of half radius, the arc will also become half, the whole diagram is symmetric. So no matter which circle you choose, you're always going to have the same angle formed at the center. And this, which we call 1 radian. Okay. So 1 radian is that angle for which the circumference, the length of the arc is equal to the radius. Okay. So arc equals, that is what we call 1 radian. So you see, this seems a bit more natural because it doesn't make any special reference to a number like 360. Because for a number like 360, somebody can ask, why not 36,000? It has even more divisors, right? But there is no logic beyond that. Okay, so most important thing now we need to figure out how do you convert back and forth between radians and degrees. So for that, if you observe, if one arc length is 1 radian, obviously two arc lengths will be 2 radians, right? So if I have an arc of twice the length, okay, 2r, then the angle formed at the center will be 2 radians. And I can take fractions also. I don't need to go into multiples, right? So the question I will ask is that how much is the total circumference of my circle? Okay, so if my total circumference of my circle is 2 pi r, and I know that this whole angle in degrees is counted as 360 degrees, right? So the correspondence of 360 degrees with this 2 pi r. And so 2 pi r is how many arc lengths? So if this is r, so how many times I have to copy this arc length of r to get 2 pi r? 2 pi times, right? So therefore 2 pi radians is 360 degrees. Okay. So I hope everybody understands this logic, that because the total circumference of my circle is 2 pi r, which we associate with 360 degrees. So therefore that comprises of 2 pi radians. Okay. And so if you understand this, then we can establish, whatever basic angles that we know, we can quickly make a table, right? So 0 radians is obviously 0 degrees. There is nothing in that. What about, as I said, 45 degrees? Pi by 2 is pi by 2. How much will pi by 2 be? If this whole thing is 2 pi, so maybe we'll do one step at a time. So half of 2 pi will be pi, right? So let's do the reverse way. So starting with 2 pi radians is 360 degrees. So half of that. So pi radians will be 180. Half of that, pi by 2 will be 90. And then pi by 4 will be 45, right? And any other special angles that we can derive? How much is 30 degrees, for example? Pi by 6, right? Because pi by 2 is 90. So upon 3. So pi by 6 is 30. 60 degrees is pi by 3. Okay. And the convention right now, I'm writing the radians symbol everywhere. But after a while, we'll get tired of writing. So we'll just write pi by 3. And from context, it will be clear that we are talking about radian. Because when I say, for example, if I write sine of pi by 4, it is understood that I'm talking about radians. Nobody is going to compute pi by 4 in degrees and find the sine of that. Okay, so it's kind of understood that we are talking about radians. So after a while, we'll get lazy and we'll not write that C everywhere. Okay, so this unit of measurement is very useful. And I hope now with this, you can find any angle in the circle in this way. For example, if I just draw this angle, so I'm talking about, let's say this is 45 degrees. So I'm talking about this angle. Always starting from the x-axis, measuring counterclockwise. So how much is this angle going to be? Mhm. No, in radians. Not 315, yeah, 315 degrees, but in the radians.
7 pi by 4.
7 pi by 4. Yes, correct. So how do you convert back and forth quickly? Or you can. Yes, correct. You can subtract pi by 4 from 2 pi. Correct. Okay. Or in general, if I can, write the formula that how much is x, any value x radians is how many degrees, and vice versa. Y degrees is how many radians. So can you come up with the formula to convert back and forth between these two? Not necessarily. I mean, for example, this angle is just one radian, right? There is no pi over here. But all the nice angles generally are multiples of pi. So actually, if you compute the value of this one radian in degrees, it's a irrational number, some very big number. I think it's roughly 57 degrees and some point something. Okay, 57 point infinite recurring, no, not recurring, non-recurring decimal. Okay, but so what is this formula? Can you see that if I have x radians and I want to convert that to degrees, what should I multiply or divide by? Just as you know, your normal units of conversion, you have this, right? To convert grams into kilograms, you multiply by 1,000 or divide by 1,000. 360 by 2 pi, correct. So basically from this you get all up, or 180 by pi, either way is fine. Okay, so 180 by pi. So x radians will be equal to 180 by pi into x degrees, and reverse. Y degrees will be equal to pi by 180 radians. So this constant of multiplication 180 by pi, if you want to remember, you can do that. Okay? But after a while, once you start working with angles, all of this will become natural to you. You don't have to think of it that way. When I say pi by 4, immediately 45 degrees will come to your mind. Okay. So as such, this is not strictly required for doing trigonometry, but it's useful to know that this is an important part of how trigonometry is defined. Okay. So coordinate geometry, two versions of coordinate geometry: normal Cartesian geometry and polar coordinate geometry, and this radian definition. These three ingredients we require to do what I'll call college geometry, college geometry version of trigonometry. So what we saw earlier was the school geometry version where we only had acute angle triangles, but now we are going to be able to define sine theta cos theta for any angle. Okay, so how do we do that? So this is how the definition goes. So first, it's like a recipe. So first, consider the standard unit circle in the xy coordinate plane. Okay, so what is the meaning of standard unit circle? So unit circle means any circle of radius 1, and standard means that the center is at the origin. Okay, so the origin of my system, if it's my x and y axis, then if I consider circle with the origin as my center and 1 as the radius, okay, then this is the circle I'm talking about. Okay, now let x be any real number. Okay, so I'm going to take any real number. Okay, now consider a ray. So consider a ray whose head is at the origin. So it starts at the origin, and the angle it makes with the positive x-axis is x radians. Okay, so for example, if I take some acute angle, maybe something like this. Okay, so this angle is x radians. Okay, and now let that line intersect this circle at some point P. Okay. Uh, so I'm just calling this standard unit circle gamma, and this line is, I should not use the letter R because I want to require R later on. For a what other letter? Let me use L only. So let the intersection of L and my standard unit circle be the point P. Okay, so wherever this ray and this circle intersect, firstly, do you agree they are going to intersect? Because it's a ray starting from the interior of the circle, so it will be intersecting and exactly once. Okay. So now my question to you is, this point P can be described in the two coordinate system that we have heard about. So in the polar coordinate system, what can be the recipe to reach the point P? 1 comma x radian, because I have to, starting from the positive x axis, first I have to run anti-clockwise with x radian, and then I have to travel a distance of 1 exactly, because any point on the circle with a distance of 1 from the center, right? So therefore the polar coordinate of this point is 1 x radians, 1 angle. Okay. Okay. And what about the normal Cartesian coordinates? And I should not have used the letter x here because we use x and y for our coordinate system. Maybe I should have used it theta, but okay, doesn't matter. So what is the normal coordinate of this point? Correct. What is cos of x and sine of x. Okay. So if you look at, if I draw the perpendicular from this to this side, and again I want to describe the recipe that starting from this point, how do I reach the point P? So the way I do it is I need to first travel like this, and then I have to travel like this. And so I need to tell how much distance I have to travel, right? So how much is this distance, this horizontal distance first? It, because in this triangle, right? If I give this point name A, then OAP, what is cos theta and what is sine theta? So cos of x. Cos of x is adjacent side upon hypotenuse, right? So OA upon OP, right? But OP is 1 because we are talking about the radius of 1. So basically OP will not matter. So only OA matters. So basically this OA distance will be cos of x, right? And what about AP? AP will be sine of x, right? Because that is opposite angle to x radian upon hypotenuse, right? Okay. So this is how I define the trigonometric ratios. Here, because we had seen the school geometry version, we sort of derived that this is cos theta and this is sine theta. But now I'm reversing the situation. What I'm saying is that whatever is the coordinate of P, the x coordinate we will call as cos of this angle, and the y coordinate we will call as the sine of that angle. Okay, so I'm sort of reversing the idea here. So I define, and let me call it theta really. It's really confusing. So wherever I've written x, just change that to theta. Okay. So now I say that we define cos of theta as the x coordinate of P and sine theta as the y coordinate. Okay. So understand and appreciate how this definition of the trigonometric ratios was motivated by the two coordinate systems coming together, the polar coordinate system and the Cartesian coordinate system. They are both simultaneously existing in the same diagram. So do you immediately see the benefit of this approach? Firstly, do you see this definition is consistent with our school geometry version? For acute angles, there is no difference, right? Whether you use that opposite side upon hypotenuse version or this x coordinate, y coordinate version, you are going to get the same answer. But now, do you see now I can define sine of 135 degrees? Because there is nothing stopping me from taking this angle beyond this 90 degrees now. So can you tell me how much is 135 sine and cos of 135 degrees now? So what will the diagram look like? I'm starting from the origin. This is my positive x-axis, which is like the 0 degrees, right? Zero degree or 0 radian line. Then from here, I'm going to go anti-clockwise 135 degrees. So where am I going to land? It's somewhere here, right? In the top left half of the plane. In fact, I'll be exactly bisecting these two axes, right? Right. And so now wherever that ray intersects my circle, I need to look at the coordinates of that point. Right. So how do I find the coordinates of this point? Because I know this angle is 45, right? This angle is 135. So this angle is 45. And to find the coordinates, again, I need the recipe that starting from the origin, how much do I need to travel along the x-axis and how much do I need to travel along the y-axis? So to reach this point, where should I reach first before I reach the point P? See, in the polar system, you just rotate and you go directly like that. But in the xy coordinate plane, you cannot do that. You have to first travel along the x-axis and then you travel along the y-axis. So along the x-axis, how much do you need to travel? Oh, sorry. I did not mean to travel that way. Yeah. This much, like wherever, if I drop the altitude, right? So wherever that lands, so this is the distance I need to travel along x-axis first, and then I need to travel this much along y-axis. So how much are these distances? No, but in terms of numbers, can I find what is the length of those segments? 1 by root 2, right? So the lengths are 1 by root 2, but remember the sign. So here, because I'm traveling opposite to the positive direction, I should say minus, right? So this is actually minus 1 by root 2. Okay, because it is, because by convention, I'm saying this is the positive x direction and this is the negative x direction. And similarly, this is the positive y direction and this is the negative y direction. So this first coordinate is minus 1 by root 2. And what is the second coordinate? Plus 1 by root 2. Okay, so the coordinate of this point P is minus 1 by root 2, comma, plus 1 by root 2. And therefore, what I said by the definition that we have created now, I'm going to call this as the cos of that angle, cos of 135, this angle, right? And this is sine of 135. Okay, so cos of 135 degrees, or if you want to put in terms of radians, you can do that also. So this is nothing but 3 pi by 4. Okay. So this is also the same as cos of 3 pi by 4. And again, as I said, we are going to be lazy and not write radians every time. So no, whichever version you want, it's okay. They are both equal to minus 1 by root 2. And what about sine? Sine of 135 degrees or sine of 3 pi by 4 is 1 by root 2. Okay, understood? So practice this for a few more times. Take various angles in the plane. Like for example, I'll just ask 3, 4 questions over here. I'll give you some time to think and work out the details. Okay. Any doubts in what we did here? How we approached it? So to actually find the length, we used normal school geometry, which is fine. But the definition we are using is that we call this as the cos and this as the sine. Okay. So uh, so try to solve these questions now. And to make things deliberately look confusing, I'm going to use sometimes degrees, sometimes radians. But the context is clear. When I'm using any multiple of pi, it is always radians. Okay. We never talk about pi degrees because that is not a very useful consideration. So for example, tell me how much is sine of 1 degrees. I'm just changing question 3 to cos. Okay, have you found this? So how much is the first one? How much? Root 3 by 2. Correct. So how do we find this? Again, draw the standard diagram. Take the 120-degree angle. And if you look at this point, we are looking at the, for the sine, we need the y coordinate, right? So y coordinate means this displacement. And so by standard 30, 60, 90 thing, you know that is root 3 by 2. How much is the second one? 0. Okay, why? Because how much is this angle? 3 pi by 2. So 270 degrees. Basically, you can think of it this way. It is pi and pi by 2, right? So pi is 180 degrees and then another pi by 2. So 370 degrees. So the ray that we are talking about is this one. And so where it intersects the circle at this point. So what are the coordinates of this point? So firstly, how much do you have to travel in the x direction? Nothing at all because already aligned, right? So the coordinate of this, the x coordinate is 0 and y coordinate is -1. So therefore, this is 0. And if I had asked about the sine would be -1. Okay. Third one. So where 240 degrees, right? So that is 180 degrees plus 60 degrees. So something like this, right? So this is 60. So this point, we are interested in the x coordinate of this point. So by the way, you notice something that the x coordinate of this point and this point will be identical. Okay. So here I asked about the sine, but if I ask the cos of 120 degrees, you see this answer and this answer is going to be equal. Because the cos is just the x coordinate, right? So cos is just this displacement, which is the same over here also. And that is -1/2, right? And you see that in fact, if you have any pair of angles which are symmetric about x-axis, their x coordinate will be same, right? So in fact, any angle theta, if I take, then how much should be the corresponding reverse angle? Like its mirror image. How much is this angle going to be? 360 minus theta, correct? So in fact, what you have is cos of theta equals cos of 360 minus theta. Okay, but there is one more thing which I didn't mention. Just as anti-clockwise means positive, clockwise means negative. So the same angle can be also written as just minus theta. Okay. Let me just clear up the diagram to explain this properly. So the same angle can be written in multiple ways. So if I'm talking about some angle over here, okay. So the normal way that we know, we talk about this angle. If I call this positive side as alpha, okay, then this reverse way that you go clockwise from x, which in the negative direction. So that will have a negative sign, right? So if clockwise the angle is, what was it, 240 degrees, right? So plus 240 degrees is the same as minus 120 degrees also. Okay. So this is just convention. There is nothing special about anti-clockwise or clockwise direction. But when we travel clockwise, we give a minus sign. So therefore, the identity is not just cos theta equal to cos 360 minus theta. Actually, the identity is cos theta is equal to cos of minus theta. And here can be any multiple of 360, doesn't matter. Because adding or subtracting a multiple of 360 doesn't make any difference, right? You are just going round and round that many times. Okay. So in other words, the same angle has multiple different representations. By adding or subtracting a multiple of 360, you don't get a different angle. You're just getting another name for the same angle. Okay. So like this is 0, this is 90, this is 180, this is 270, this is 360, this is what, how much is 360? 450, this is 540, and so on and so forth. So every point has multiple descriptions, including negative values also. This point can also be written as minus 360. This can also be written as minus 270. So like that, both positive and negative angles are allowed. Okay. And what about the fourth one? Root 3 by 2, right? Because again, you get a 30, 60, 90 triangle. Minus root 3 by 2, right? Because it is in the second quadrant. Okay. So again, spend some time practicing this at home, that, try various ratios of pi, or, what are well-known angles that you know. And can you find the sine theta, cos theta, all those things. Okay. And actually, there is a whole table of such properties, like what I wrote here about cos theta, right? Cos of theta is equal to, so let me write it more properly. Cos of theta is equal to cos of minus theta, but which is also equal to cos of 360 minus theta, 720 minus theta, or in general, cos of any multiple of 360. You can take any integer multiple of 360, you can add or subtract, it doesn't make a difference to any term, in fact. And anywhere you add or subtract a multiple of 360 degrees, it will not make any difference. Either 360 degrees or 2 pi radians, right? So 2 pi n, same thing. Okay, so let us look at one application of this, that, okay, we generalize the school geometry version to the college geometry version, but what the benefit that would give us? It allows us to define angles of greater than 180 degrees, 90 degrees, or even negative angles also. I can write the sine, cosine, which is very good. But does it help me in any way? So do you know the extension of Pythagoras theorem for non-right angle triangles? And there are two versions of it, right? For acute angle triangle, it is slightly different, and for obtuse angle triangle, it is slightly different, right? So what this notation will allow us to do is to combine those two into a single theorem. Okay, so let us look at that. So first, of course, in a right angle triangle, we have, if I call this not general notation, but generally a square is equal to b square plus c square. This is the right angle triangle. In the acute angle triangle, what do we have? So how do I write a square is equal to b square plus c square? But because it is acute, so I have added extra, right? So I need to subtract something. So how much is the quantity that we subtract? If I drop this altitude d, then how much do we subtract? 2 into dA into d. Correct? And for obtuse angle triangle, again, now if I write a square equal to b square plus c square, I'm actually under counting. So I need to add something more. So how much do I add? 2 times AD into AB, right? So, and maybe I should write it here. Okay. So if I look at this statement, this statement, this statement, it looks like I'm talking about three different theorems. But now we are going to see that actually all of them are special cases of one common theorem. Because let us look at this term more closely. Let us look at acute angle triangle and this term. So can I replace AD by something else? So this AD, which right angle triangle is AD part of ADC, right? So if I call this angle capital A, then how much is AD? Or rather, I say how much is cos of A? Cos of A is adjacent side upon hypotenuse. So AD upon AC, right? Correct. And therefore, I can write AD as equal to AC times cos A. Okay. So if I make that substitution, what will my new statement look like? So I'll write A square is equal to B square plus C square minus 2 times AB into AC into cos of A, correct? And instead of AB and AC, I can use the same notation, right? Small c and small b. So I can write in fact as this is 2 times BC into cos A. Okay. But now what I'm asking you to see is, do you see this same statement is true for the remaining two cases also? Take the 90-degree case. So now here this angle A is 90 degrees, right? So how much is cos of 90 degrees? It's 0. What is cos of 90 degrees? You start at the origin, you go 90 degrees, you reach this point, and what is the x coordinate of this point? 0. So naturally that term goes away and we get Pythagoras theorem. And for obtuse angle triangle, yes, what happens is that when I am saying cos A, I'm talking about this angle, right? Which is an angle greater than 90 degrees. So from the examples that we saw earlier, or you can see that if your angle greater than 90 degrees, from 90 to 180, any angle that you take, its x coordinate will be going to be negative because it goes into that second quadrant. Okay. So therefore, this cos is negative, but there is one minus sign here also. So what will happen? Minus minus will become plus. And so that what was the minus sign in my original statement will become the plus sign over here. Okay. So this statement is true for all triangles. Let it be right angled, acute, or obtuse. Okay. And look at how that statement is constructed also. It is a very natural statement. I want to find the length of one side. Okay. In this diagram, I have to find the length of BC square or BC rather. So what I need to know to compute that, I need to know the adjacent side lengths, right? B and C. So B and C are required. And I need to know the angle found between those two, right? So these three pieces of information are required. Anytime I know the two side lengths and the angle between them, I can find the third side. So if you think about, this is a very powerful tool because this situation you land in so many times when you have enough information to describe the full triangle, right? That you have all the three components required and you want to find the third side. Okay. Or you can do the reverse also. Suppose you know the three sides of the triangle. Can you find the cos of A now? Just by reversing this, right? If I just rewrite this, take cos A to one side and to put everything else on the other side, I can find cos A in terms of the remaining three sides. Okay. So just write that formulation also because sometimes one is useful, sometimes the other is useful. Okay. So the normal, so this is called cosine rule, by the way. So this is normal way of writing it. And if I just rearrange this, I can write cos of A is equal to so this is called and you see how it nicely combines what we initially in school geometry thought were three special cases like right angle triangle, obtuse angle, and acute angle. But now single statement is covering all three. So this is an exercise for you to go home and verify that the obtuse angle case I did not analyze fully, but make sure you do that and sort of make it clear to yourself that really this is the same statement and all the angles are matching, everything is matching. Just verify that properly. Okay. So as I also mentioned last time that cosine rule and sine rule, these are the two basic things that we need to know for our purposes for Olympiad as such, at least at initial stages. If you go to more advanced application, then you need a lot more formulae also. But today it's not important to cover them. So this is cosine rule and sine rule I already talked about last time, but let me just mention it once more. Okay. So sine rule is nothing but if you have a circle and you know its radius and you want to find the length of a chord. Okay. So I want to find the length of some particular chord. And what I know is the angle formed by that chord. So I know this angle theta. So my question is how much is the length of this chord? Okay. So that question gets answered by sine rule. Okay. And how do you do that? If you join this chord to the center of my circle, then we know that this central angle is 2 theta. And so if I again drop altitude, then each part is theta. Correct. And so in this triangle, in triangle OAB, I can write sine theta as how much? Opposite side, that is AB upon hypotenuse. Right. And so if I want to find, so I know AB now, and AC is just going to be twice of that. So therefore I get AC as 2 times AB, which is 2 times R times sine of theta. So this is sine rule. Or another way of, so sine rule has many different variations. So one way of expressing it is this way. You say I can rearrange this and also say that therefore equivalent to this, I can also say that no matter which chord I take in my circle, the ratio of the chord length upon sine of that angle is constant. No matter which chord you take and which, of course, the angle is equal, right? No matter which angle you inscribe, they are all theta. So what I'm saying is that in this circle, if I take a different chord and if I take the angle opposite to that, okay, if I call that theta 2. So this is the length of second chord and this angle is theta 2. And again, I compute this ratio, the length of the chord upon sine of that theta. That will also turn out to be the same, 2r, right? So this ratio is always going to be 2r. So in other words, the length of the chord and the sine of the opposite angle are always in the proportion. Theta should not, see, theta anyway doesn't, if your chord length changes, then theta will change. But even if both are changing together, right? So this ratio does not change. That's what we are saying. And so the most useful case where this can be interpreted is in a triangle. So in a triangle, what happens? Suppose I take a circumcircle of my triangle. Okay. And so now I can see pairwise, I can take one side and opposite angle, right? So like that, what are the pairs which I get? And like kind of overuse of notation that we call the same angle as the same vertex. So the same letter to denote the angle as well as the vertex. So therefore the length of one chord, so BC is the chord divided by the sine of the opposite angle equals that. So you see every pair of length and opposite angle, that ratio is 2r. And now this only you can rearrange to say that, and by convention we denote this by small a, small b, small c. So this can be even simply written as a upon sine a equals small b upon sine b equals small c upon sine c. And therefore, if you cross multiply, you get things such as small a times sine b equals small b times sine a. So whenever if you take only one pair of sides, right, a and b, and the opposite angles to that, then you can do this kind of crisscross. A times sine b is the same as b times sine. And you see one more reason why this is true. If you look at the diagram and look at a times sine b, what is this representing? If I want to use the very basic definition of sine.
So altitude from C to AB.
Yes, correct. If I draw this altitude from C to AB, then I'm going to get one right angle triangle over here. And in that right angle triangle, how much is sine B? This altitude length upon small a, right? So actually, this is equal to b times sine A is equal to the length of that altitude, h of c. Okay, do you see that? If I just rearrange, if I take a small a to the other side, I see sine of capital B is equal to hc upon small a. So all of these are like alternate ways of saying the sine rule. Depending on the context, you will use one of these formulations. So either you talk in terms of the chord, the length of the chord and the inscribed angle, or you talk in terms of the ratio of that chord and that inscribed angle, or you talk in terms of the, in a triangle, you're talking about all the three combined together, or you're talking about only one pair of opposite sides. But really, it's the same thing, sort of reorganized in different ways. It's not really different. So all of these together can be called the sine rule. I don't want to say that this is the sine rule. Sorry, can you repeat that? A times sine B. Yes, correct. So because of this fact that the height altitude is given by this a times sine b, so I can use that to come up with one more formula for the area of the triangle, right? Because I know the area of the triangle is half base into height. So if I multiply this by c on both sides, then I'm going to get, in fact, c by 2, I should say. Then on the right side I'll get c times hc upon 2, which is half base into height, which is the area of the triangle, and therefore which is going to be equal to, for example, if I multiply this, so it is going to be into c by 2 sine A. So again, you see how that this is formulated, that in any triangle, if I know the lengths of two sides and the angle between them, I can find the area of the triangle as half into product of those sides into sine of that angle. And again, you'll see that in the, if this angle happens to be 90 degrees, then sine A goes away because sine of 90 is 1. So then that in the right angle triangle, we know that the product of the two sides upon 2 is the area of my triangle. Okay. So I understand, I'm uh, talking about a lot of information in very little time, but that is how the topic is. I mean, we cannot take 3-4 lectures to cover trigonometry, but I'll suggest go back, go home and again revise this more properly. As you know, the recording is always available on YouTube. So um, slow it down and see it piece by piece so that make sure you understand all the parts properly. Any doubts you can refer to me, or all of this is standard theory. So any textbook also you can refer to if you want. Okay. Okay. So this was what I'll say the college geometry version of trigonometry. Okay. So far we have seen two versions. One is the school geometry. So now having seen all of this, you realize that school geometry was a very small part of the iceberg. It was like the tip of the iceberg. And so now we have seen college geometry version. Okay. But that geometry is also tip of another iceberg. There is even more to it than this. So there's another aspect of geometry, trigonometry, which is algebra. Okay. So even algebra can also be used to look at this sine theta, cos theta in a different way. So for example, let us do this. If I plot a graph of sine theta versus theta, like a XY plot, as the angle changes, how does the sine change? Okay, let us draw this graph. Okay. So it will look something like this. And this is a very convenient way of drawing this diagram. But let me take a new page. So here what I'll do, on the left hand side, I'll draw a standard unit circle. And on the right hand side, I'll actually draw the graph which I'm interested in. Okay. So the convention is this: in my graph, the x the x-axis denotes the angle theta, and the y-axis denotes the sine of that angle theta. Okay. So for example, when my theta is at 0 degrees, okay. So how much is sine theta? Sine is the y coordinate, right? So y coordinate you can understand as how much is the altitude from the y, the x-axis, right? The vertical displacement is what we call the sine. So at 0 degrees, the sine is 0, right? So we are somewhere here. Now, as the angle increases, right? You see this vertical height will keep on increasing, right? So the sine is going to increase. Will it keep on increasing or where it will reach the maximum? 90 degrees, right? So when my point reaches here, that is where my sine theta is at the maximum. So if I draw the graph of just this portion, it will look something like this. So this is at 0 degrees. Let us say this is at my 90 degrees. Okay. So at 90 degrees, so the graph looks something like this. After that, what will happen? When my angle goes beyond 90 degrees, you see the y coordinate will start decreasing now. This vertical height is going to decrease. It's still positive, but it is reducing now. And when I finally reach 180 degrees, that value will become 0 again, correct? So that part of the graph will look something like this. So at this point, I return back to 0. But I can keep going, right? So beyond 180 degrees, if I go, what will happen? It will go into the negative half, right? So if I have an angle like this, now my displacement is in the negative y direction. So my sign is reversed now. Right? So from this part, from 180 degrees up to 270 degrees, my value will keep on decreasing. At this point, it will reach the lowest value, right? It cannot go below this. So the graph will look something like this. So this is 270 degrees. And finally, after that, what will happen? It will come back to 0, right? So have you seen this graph anywhere? This kind of a, this is what we call a sine wave. Have you heard this term? This shape, this is called a sine wave. Okay. And I stopped here, but you will see I can keep going because as you already said that if I go beyond 360 degrees, I'm just going to keep repeating the same pattern. Okay. So if I wanted to continue this graph further, it will look something like this. It will keep on oscillating, right? It will keep on going this way. So and so on and so forth. So if I zoom out, if I draw the graph at a slightly different resolution, it may look something like this. And even negative angles. So this is what that graph looks like. Okay. So this is called a sine wave. So actually this sine wave is a very basic building block of many things, not just in geometry, but in algebra, in physics, in engineering, everywhere you are going to encounter this sine wave. One very interesting thing we are going to do is, you have calculators, they calculate sine theta. How do they do it? Do they take a ruler and compass? They draw an angle, they measure the x coordinate. They cannot, inside the calculator, there is no person sitting with a geometry box, right? So how do they compute sine theta? So this is how they compute it. And I'm just going to show this to you as a, illustration of something interesting you can do. But we don't know enough mathematics to write the proof of this, but we can still enjoy how this works. And I wish I had a keyboard to type this, but okay, we can manage. Okay, so this is the normal coordinate system. And so let us first draw the graph of sine of x. So you see, I'm getting the sine wave which I talked about. This is the sine wave. Okay. So interestingly, if you look very close to the origin, right, it almost looks like a vertical, like straight line. Like from a distance, you see it has a lot of curvature, but suppose you zoom in only to this part, you'll see that almost it looks like a straight line. And in fact, if you look closely, what do you think is the slope of that line? If I zoom in, zoom towards, it looks roughly like 45-degree line. So very close to this region, if I wanted to approximate the sine value, I can just say sine of x is equal to x. If I just, let me just plot the graph of x. You see this blue line, which is the simply y equal to x line, and the sine theta is not so bad. Close to the origin, it almost looks identical. But of course, when you go farther and farther from the origin, the values are not same. So what I need to do, I need to add some adjustment term. Okay. So here, if you let us look at the positive side. So where this y equal to x line is going above the sign. So do I need to add or subtract something? I need to subtract something, right, from this x, but I will get this sine value. So how much do I need to subtract? So I'm going to subtract. And so this is the part where I cannot explain why this term comes. Sorry. Why is the cursor going to places? Like just type it. So I'll take x and I'll subtract x cube. Okay. So if I subtract x cube, what do I get? Okay, it looks like slightly, it is now starting to look like a sine wave, but not perfectly, right? It seems that this is dropping out much quicker and this green wave is continuing for longer. So let us not subtract x cube, but I'll just subtract look at this orange one. You see the orange line is now slightly closer to my sine wave, the green line, but only up to a point. After that, it seems to go away again. But now do you see, now we are below the sine wave. So I need to add something. So I sort of like inclusion exclusion. Do you know how you add something, then you subtract something again, you have to add. So you have to keep adjusting terms that way. So now I need to add something. So now let me add. The blue line represents the original x, y equal to x. The original, the g of x, which is the original one, right? First attempt that we did to describe sine theta. So we close to the origin, we thought that just we can write the function as y equal to x. So that was the blue line. Then to add to that, we added one more term, this x cube upon 6. This is that orange. It's a polynomial. It's a match with the green wave. We have to match with the green wave. That's the sine theta, right? So now what I need to do, I'll subtract x cube once more upon 6. And now to that, I will add one term. And do you see the pattern over here? Why did I write 120? So this is purple line. You see that purple line is coming even closer to the sine wave. Like in particular, if I zoom out from a distance, you see that this purple line and the green are matching even more and more. So compared to the blue one, this purple is even closer, right? And you see the pattern. Can you guess what should be the next term?
Minus x raised to 7 by 7 factorial.
Upon what should be the denominator?
7 factorial.
7 factorial. You see, this is 3 factorial, 5 factorial. So next term will be 7 factorial. And as such, every time I add one term, I'm getting closer to my exact equation, but I'm never getting exactly there. So to get exactly the sine wave, I have to add infinitely many such terms actually. Okay.
Sir, what is the reason you chose x cube upon 6?
Yeah, that's what I cannot explain it right now because we don't have enough background knowledge to do that. But this is how your calculator does it. What calculator does it, it computes enough terms until that difference becomes so small that we don't care. After a while, that difference between the actual sign of x and your polynomial will be in the fifth or sixth decimal place. So at that point, you can disregard the remaining terms. So depending on what is your requirement, you will take those many terms of accuracy. Like for somebody, for me, it is enough to approximate sign as simply x minus x cube by 6. Then I'll use this version. Somebody needs more precision, they'll use this version. Somebody needs even more precision, they will add more terms. Okay. But this, you can keep adding as many terms as you want. Okay. So just to write it again. Okay. So again, we cannot prove this today, but just want to state that. So sine of x can be written as the sum of this infinite series x. So implicit was there x raised to 1 upon 1 factorial, if we did not write actually, minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial. Is infinite sum. So firstly, we need to understand what do you mean by adding infinitely many terms. What is the definition of that? That itself we don't know. We know how to add finitely many objects, but what is the meaning of adding an infinitely many values? So there are lots of things that you need to know before we start to understand this. And so if you want to study this properly, you have to study some limits, continuity, calculus. And the topic of this is called Taylor series or Taylor expansion. So just like sine of x has this expansion, cos has this expansion. Every function that you know has a similar expansion. Okay. Logarithm also has, exponential has, all of them have some expansion like this. Okay. So now the question that you may be wondering is that why this expression has nothing to do with geometry. It has nothing to do with right angle triangle. It has nothing to do with the standard unit circle. So what is the guarantee that the value you get using this expression is the same as the one which we did in the previous two sections, like school geometry and college geometry? So that is something, is an open question for you to figure out the answer. Okay. But this is one more way of describing sine of x. Okay. So there is one more way of describing sine of x, which is through physics. Okay. So the third description was algebra. Now the fourth description is physics. You can do this experiment if you want. Do you have a pendulum clock at home? If anybody. Okay, just look at the pendulum, or you must have observed it somewhere, right? How pendulum swings, right? So imagine that a pendulum is swinging like this, right? It keeps real life pendulum comes to a stop at some point. But imagine ideal situation where the pendulum keeps swinging. Okay, and imagine that you attach some kind of a pen or pencil to the pendulum. Okay, so as it is swinging, it is also going to make lines, right? So it is going to keep making a line on the paper below it, let us say. Okay, and suppose at the same time I keep moving that piece of paper in one direction. Okay, so as the line is, otherwise it will keep tracing the same line back and forth in the same place, right? But I want to see as a function of time, how is that position changing? So I set up a situation where there is some paper which keeps on shifting with some constant speed, so that as the pendulum is swinging, I'll get a trace on the paper. And as you can imagine now, everything that we've done, that what that trace looks like is something like this. So what that pendulum describes is a sine wave actually. As the pendulum goes back and forth between its extreme positions, what it describes is actually a sine wave. Not just a pendulum, if you take a spring, okay? So if I take a spring, so this is something that you will do in your 11th standard JE physics, that if you have an object, like this is a mass and this is a spring attached, and let us say this is a normal situation where the spring is neither stretched nor compressed. Okay. And now what will I do? Suppose I take this object and move it slightly to the right. Okay. So I stretch the spring and then I leave it. Then what will happen? The spring will pull that mass together, too close to itself. but it will pull so fast that it will cause the spring to compress, right? It will not come to a halt exactly at this position. So it will overshoot. And so that actually it will cause the spring to get compressed. And after that, what will happen? Again, the spring will try to expand. And so this will keep on happening. So, this mass will keep oscillating back and forth between these two positions. And again, if I draw the plot of that position versus time, it is a sine wave. And so on and so forth. I mean, in physics, you will find examples of sine wave in every place. For example, uh, light and sound waves. Why do we call them waves? Because actually they are sine waves. So whatever light is getting emitted from the tube light and reaching me, if I have very sensitive electric field meter, and if I see how much is the oscillation of that light particle, I'm going to get a sine wave. So either electric meter or magnetometer, I'll again get a sine wave. So pretty much every field around you that you see, you are going to encounter sine waves. And actually, sine waves are important for me also, because as an engineer, so this was physics. Let us come to engineering for a moment. Okay. So we looked at this problem a few weeks ago, actually, about how to send information efficiently. That if I want to tell some information to another person, I talked about how I can write that ABCD as bits like 0001 and send those bits and things like that. In the same way, right now we have how many people? 10, 11 people on Zoom right now who are all able to see my lecture live. How is that possible? Because of sine wave. So let me explain how. Let me take a very simple example. Okay. Let us say I have a grid of 4 numbers. Okay. Let me say the numbers are 10, 11, 12, and 13. Okay. And I want to send this information to you. Okay. And let us say that for every number, like I need to spend some energy, right, to send this information to you. So if I want to send this whole information to you, I have to spend, let us say, I add up all the numbers, and that total is how much energy I need to spend. Okay, that is not how it works, but just for simplification. So if I have to send this information, how much energy I need to spend? This much, right? So 23, 46. So I need to spend 46 energy tokens, let us say, okay, to send this information to you. But now let us do this. I'm going to give you 4, what we can say, um, like building blocks, like Lego. Suppose I give you these 4 building blocks, okay? Okay. So if I call these building blocks A, B, C, D, okay? A, B, C, D. And if I ask you, I'm going to do this operation. I'm going to take each building block, multiply it with some constant. So suppose X times this block plus Y times this block plus Z times this block plus W times this block. And when I say multiply this, I'm going to multiply all the coefficients with that value, right? So I'm going to multiply all of them by that value. And then when I add up, I'll be doing it component wise, right? So the top left will get added to the top left like that. So like that, can you work out the values of X, Y, Z, W so that the sum of all this is going to become this?
So they can be negative also, right?
Sorry.
They can be negative also, right?
Yeah, XYZW can be negative also. No problem. Okay. So if I can write the equations one component at a time. So if I look at just the top left coordinate, this 10 will be equal to x times 1, correct? Plus y times 1 plus z times 1 plus w times 2. So 10 will be the sum of all the four. Then if I look at the top right coordinate, 11 will be equal to just x and y, right? Then 12 will be simply x plus z. And finally, 13 will be x plus w, right? So I'm curious to know, how do you efficiently solve a system like this? Firstly, do see it is very symmetric that x is there in all the places and other variables y, z, w are coming exactly once. So how do you solve this quickly? And it's a useful skill for your PRMO kind of thing where time is of the essence. So if you take your time to eliminate one variable at a time, it will take a lot of time. So how do you quickly solve a system like this?
They were in the first equation and x plus y. So you get 10 is equal to 11 plus 10 plus 2.
Okay.
And then add equation 3 and 4, you get 13 plus 12 is equal to 2x plus z plus w. Then we can use the value from the first equation of z plus w.
Okay. Okay.
We can add the last equation.
Yes, correct.
Yes, and then subtract the first from the third, and then we get the value of the x.
Yes. Yeah. So both approaches are valid. I think this is slightly faster. At least it's easier to understand. So what we can do, let us just add all the three equations together. So we'll immediately get 36 is equal to 3x plus y plus z plus w, right? And you see that y plus z plus w is already here. So therefore, it directly you will get the value of x, right? So how much is x going to be? So I'm going to get 26, x is equal to 2x. Oh, sorry, 26 is equal to 2x. So therefore, x is 13. Okay. And once you have x, then y, z, w can be easily computed, right? From this. So x is 13. How much is y? Minus 2. Z is minus 1. And w is 0. Okay. So again, I'm going to illustrate some different point, but as part of this, understand how to do these kind of calculations quickly. Okay. They will save you time in an exam. So what I'm going to do now, instead of sending this matrix, right? Sorry. Instead of sending this matrix, I'm going to send this x, y, z, w value. So instead of that, I'm going to send this matrix instead. So I'm going to write x, y, z, w here. So I will write 13 minus 2 minus 1 and 0. And now if you add up this much, like how much energy I need to spend to send this. And like negative, you can ignore a sign. So just magnitude. So this is 13 plus 2 plus 1, which is 16. So the original, if you wanted to send this information, you would have required 46 energy tokens. Instead of that, I can send the same information in just 16 energy bits tokens. Okay. And do you understand that whoever receives that information, once they receive this matrix, and they already know that this ABCD of matrices what I want to use. So can they reconstruct the original matrix now? All they have to do is they have to multiply this ABCD with those coefficients and add them to get back the original matrix. Okay, so this was a small illustration because we had to do the calculations by hand. But actually, when I'm talking, the camera is recording what I'm saying. The image is coming inside the memory of the photo sensor. What it is doing, it is dividing that image into blocks of pictures. Each block is getting transformed through this into, so this is what we call the transform coefficients. Okay. So whatever are these values x, y, z, w, they are the coefficients. So this is called a transform. That I start from one version of my information. I do some calculations. I get one more version of the same information. So what the camera is doing is what we call a transform. And then this information is sent over the wire to whoever is watching the video. And at their end, their monitor or their CPU is going to do what we call the inverse transform. So the inverse means reciprocal, right? So whatever operation we had to do to get from point A to point B, if I reverse that, that is the inverse transform. And that is what their monitor or CPU is doing to get back the original information. And this is not theoretical. This is actually happening right now, like 30 times per second. Like even as I speak already, when I started to explain this to the point where I've stopped explaining, already this calculation has happened maybe a few million times. Okay, so this is a real process which is happening right now. Okay, and if you're interested to read more about this, and so important thing is what are these blocks? You know, these building blocks are the important thing, right? Because if I choose them carefully, then I can minimize the energy required to transmit. So the question is, how should I choose these building blocks to get that energy as low as possible? So one common choice for the building blocks is sine waves. And you see, if I just Google this, there is so much information online. I can pick any one of them. Where did that image go? Yes. So what you see here are those building blocks for an 8 by 8 image. So if I divide my original image into blocks of 8 by 8 smaller images, and then I have to figure out the coefficients by which I have to multiply each of these blocks. And you see that top block is like by 1111 block because all the values are same. But now apart from that, for every block, do you see that there is like sine wave kind of pattern, periodic pattern. And along this first row, you'll see that all the patterns are horizontal. Along this first column, you'll see all the patterns are vertical. And then every other, you see the checkerboard pattern everywhere, where combination of horizontal and vertical is coming. And so this represents those 64 like matrix operations, which when multiplied with right coefficients and sent to the other person, they can decode it and get the original image back. Okay. So, and as you can see, sine, cos. So this is called a discrete cosine transform. Actually, this operation of what we did is called a discrete cosine transform. And that cosine is the same cos that we have talked about. And you see pi is coming everywhere. Why is the pi in that expression? Because everything is being done in radians. Okay, so understand that what we did today are the most important foundational blocks of whatever engineering discipline you are going to pursue in the future. Okay, or even if you are going to do pure mathematics, you are going to deal with sine waves in a very important way. As it so happens, my own BTech final year thesis was based on sine waves, but I cannot talk about that right now. Actually, it is related to this topic in a very interesting way. So, you know, sine wave is, if you ever try to hear a sine wave, you will hear a tone, like a constant tone, like a beep, you know, on the phone, have you heard this kind of a beep? Please leave a message after a beep. When that beep comes to that small segment, that is actually a sine wave being playing for 1 second. Okay. And so if I keep playing it for a long time, it will like a not a very pleasant sound, actually, that kind of a very harsh sound that keeps playing for a long time. But actually what birds, when you hear the twitter of birds, right? When a bird speaks, so to say, they are also emitting sound wave, like a sine wave. Only difference is that sine wave frequency changes over time. So they start with a low pitch sound, like that kind of a low to high transition is there when a bird tweets. So that it's a sine wave, but that sine wave looks something like this actually. So it is not. The graph which I showed earlier was a sine wave like this. But when a bird tweets, that sine wave looks something like this. So it starts like this, but then it becomes faster and faster and faster. So the speed of that sine wave variation is not constant. It changes over time. Okay, so this is called a chirp wave. Okay. And why is it called chirp wave? Because it is exactly how the birds are chirping. Okay. And this chirp wave is what a bat, you know how a bat echolocation, have you heard of how a bat finds out what is around it? It transmits a signal, it bounces off the target and it gets back that signal. So that bat is also emitting chirp waves. it is not emitting sine waves. And there is a reason why it cannot use sine waves. Just imagine like evolution trained the bat to understand that you cannot use sine waves to bounce off a target and find out where that target is. You have to use chirp waves. Okay. Uh, can anybody think of the reason why sine waves cannot be used and why you require chirp waves? No, the noise pollution will be there anyways. Okay, kind of. What about the distance? Hmm. Actually, this is what happens. So suppose the bat is over here, okay, and the same principle is applied for radar, sonar. So let us take sonar, submarine, okay. So let us say we are inside water, okay, and so this is our submarine, and this is my sonar machine, which is going to emit the wave, and there is some obstacle over here, okay. So what will happen? The wave will hit that obstacle, and it will reflect back, and I'm going to detect that reflection, and I know that where that object is positioned, okay. And these what I'm drawing the lines, they are called iso phase lines. So actually they are that whatever sine wave I drew, right? Drawing the sine wave is very tough. So what we do is we choose any one point, the topmost point of that sine wave. And if I draw a line over there, right? So these lines are what I'm drawing in my picture. Okay, just to make it simpler to draw. Okay. So this picture is fine. But now imagine what happens if like this. So my object is over here first. Okay. And so my waves are going like this, and I'm just drawing them as vertical lines, although they are slightly curved. And so they bounce back off the target and they come back like this. And I detect that. But now imagine that while I'm doing this, the target is also moving. So suppose the target is approaching us. Suppose it's a missile that the enemy has fired and it is approaching us. And now see what will happen. So I'm still going to transmit, let us say I transmit sine waves, not knowing anything. Now the first wave, when it hits, it is going to hit here and send me back. When the next wave reaches the target itself has moved slightly. So the next point of contact will not be in the same distance. The distance will be reduced. And when the next wave hits, that distance will be even further reduced. So I originally transmitted with some frequency, but my response will be actually of a much higher frequency. So if I send a pulse of maybe 100 megahertz, I will get back a pulse of maybe 200 megahertz. And that value, whether it's 100 or 200, will change depending on the speed of that object. Okay. Do you know what is called? This is called. There's a famous term for this phenomenon, that when the object itself is moving.
Doppler effect.
Doppler effect, correct? So I don't know if you have heard of this term called a Doppler effect. And it is the reason why even right now, as we are standing, there are cars passing below. If you hear the sound, as the vehicle approaches, the frequency goes up. And as the vehicle departs, the frequency goes down. Okay. If you very closely observe the sound, right now it's not possible, but you must have seen this, like that which goes, and then when the vehicle leaves, it actually dips. So when the object is approaching you, the frequency will increase. Conversely, if the objects were going away from us, then the distance between these wave fronts, it will expand. And so that distance will increase. So whatever frequency I transmit, I cannot guarantee that I will receive at the same frequency. Okay. And the chirp kind of solves this problem because chirp covers all the frequency spectrum. You see that the chirp signal is not confined to one particular frequency value, right? Like there is one part of that chirp which is at 100 megahertz. There's another part which is at 200 megahertz. There's another at 300 megahertz. So no matter what is the speed of that moving target, some part of my chirp signal will intercept that, and I will get the response. Okay. But anyway, I think we cannot formalize any of this currently because we have to do a lot of theory. These topics are typically done at third year of undergraduate engineering course. So clearly we don't have enough tools to deal with this. But I'm just giving you a glimpse that why what we are doing is important today. Like why sine theta, cos theta are important. because you are going to keep encountering these ideas in whatever mathematics that you do. And I ran out of time, but I could have also talked about one more dimension where like trigonometry is important, which is art actually. So music, uh, painting, colors, these are all places where sine theta and cos theta are very important actually. But I'll leave that for you to Google and find out more. Okay. So what is the takeaway from all of this? That finally, like trigonometry can be looked at through multiple angles. So this was the engineering part of it. This was the physics part of it. This was the algebra part of it. This expansion. This is how calculators do it. This was our college geometry version where we drew the angle in any plane. And then at the very beginning, we had the school geometry version. But all of these are like two sides of the same coin. You know this term. So these are like 10 sides of the same coin, not just two sides. Okay. And so depending on which branch you go, you are going to deal with sine waves. See, there is no escaping from sine wave. It's just that whether you do it as a mathematician, whether you do it as a physicist, whether you do it as an engineer, whether you do it as an artist or a musician, but you are going to deal with sine waves all the time. Okay. So yeah, that's all for today. As I said, next time we are going to have a practice test. I will announce more details of that in the WhatsApp group. Okay.
Then what if instead of the wave has a higher frequency than the sine wave?
See, even if it's a higher frequency, if the shape is like a sine wave, we still call it a sine wave only, right?
But what is the significance if it has a higher lower frequency?
Significance means that the tone, if you hear of that tone will sound lower or higher. That is the only significance. I mean, if I understand your question, like, I don't know, there may be some tools to.
Excuse me, sir.
Yes.
So could you just forward some article or something related to how sine waves are used in art?
Yeah, sure. So you can just Google sine wave and music. You'll
Okay.
probably. Actually, I had found one video which was very interesting. I'll talk about that. Online calculator. By the way, cover your ears if you want to. I hope they can adjust the volume. Yeah, thank you. But this number 440 is important. So you are asking about art, right, Anushka? So do you know the significance of this number 440?
No, sir.
So that is the middle A. If you play piano, you know A, B, C, D, E, F, G. The letters are given to the this. So A4, which is the middle A, is 440 hertz, and everything else is computed from that starting point. Oh, sorry, it's not playing anything. But anyway, you can go home and listen to this on your own. Or is it? I don't know. Maybe it's not working. I'll try to find some website where you can play with all of these things. Yeah. Okay, that's all. Thank you.
Right, so thank you, sir.